This video will build on the previous video which introduces the BGW process, and it will also assume a very basic understanding of differentiation. Here is everything that you will need for this video. In the last video, we are left with the second question, the probability of extinction. This translates to how likely is coronavirus eradicated under this mathematical model. To tackle this problem, we said that we can encode this table of probabilities to the generating function g. The last part of the previous video explains why the generating function for xn is just g iterated n times. Then, theoretically, we can decode this generating function to the distribution table. We are particularly interested in the probability that it is 0. This is because if xn is 0, then there are no coronavirus patients in the nth generation. But just note that it may also be the case that coronavirus has been eradicated in the previous generations. This is actually good because when we say extinction probability, we don't care about when it gets eradicated. We just care about whether eventually coronavirus will end. So in fact, more precisely, it is the probability that xn equals 0 when n tends to infinity. We know that this part can be theoretically done by the previous encoding-decoding method, but how do we do it exactly? If xn has such a distribution, then by definition, the generating function for xn looks something like this. So if we want the probability that xn equals 0, then we can just plug in z equals 0 in this formula, because everything except the constant term would be cancelled. So we have the probability to be gn of 0. Since we can relate this to g, the generating function for x1, the required probability is 0 iterated by gn times. The final probability of eradication is where n tends to infinity, or 0 iterated by g an infinite number of times. For any iteration like this, there is a very nice way to visualize what's happening. We need to construct the graph of y equals g of x, the generating function. Before we move on, we want to know the shape of this function to plot it properly, so we need to know its properties. From now on, we will only restrict our attention to the case where x is between 0 and 1 because of something called radius of convergence. In short, we are only sure that g of x is well defined in this region. Anyway, because we restrict ourselves to a non-negative range and all the coefficients, which are probabilities, are non-negative, g of x has to be non-negative for all x in this region. Next up, we have g of 1 equals 1. Why? If we plug in z to be 1, then g of 1 will just be the sum of the coefficients, which are the probabilities of all possible values of xn, so it has to add up to 1. The next couple of properties depend on a basic knowledge of differentiation. We first differentiate g of z using power rule and linearity. As we can see, all the coefficients are also non-negative, so the slope of the graph at any point is non-negative, or in other words, g is increasing. If we differentiate it one more time, then we can still see that all the coefficients are non-negative. This means that the slope itself is also increasing. With these four facts, we know that this is what the graph of a typical g of x looks like. However, we will also consider another graph, which is y equals x. This will be crucial to the visualization of the iteration process. Since g of 1 equals 1, we know that these two graphs must have at least one intersection at the point 1, 1. This is not the only possible scenario though, because they can also have two intersections, one of which is still 1, 1. But based on these four properties of the generating function, these two cases will happen most of the time. The only exception would be where the graph of g coincides exactly with the straight line. Since it is just one simple case, we will leave this out of discussion for now. We first focus on this case where there are two intersections, and recall the objective here. The extinction probability is 0 iterated by g n times. Let's focus on this lower part of the graph. Notice that the y-intercept would be g of 0. Next, we go to the right so that both coordinates are now g of 0. Then we go upward so that we get the function value at g of 0, which is now g of 0. This completes one iteration of g. What we want is an infinite number of iterations, so we will do this process a lot more times. Eventually, we will get to this intersection point here, where the coordinates x or y, because they are the same anyway, represent the probability of coronavirus eradication. In this case, the probability is less than 1, because the intersection 1, 1 is somewhere else. This technique of visualizing iteration is generally known as cobwebbing. However, in the other case, there is only one intersection. Applying the cobwebbing technique, it will converge to the only intersection, which is 1, 1. And so, the extinction probability in this case is exactly 1. Comparing these two cases, we can generalize the conclusions to be this. The extinction probability is the coordinate, either one, of earliest intersection. This is also applicable to the special case. Anyway, what is the fundamental difference between these two cases? Can we not plot the graph but still say definitively which case we are in? The trick is to see the slope of g of x at the point 1, 1. If the slope is smaller than or equal to 1, we will be in this case, and the extinction probability is 1. If the slope is larger than 1, we will be in the other case, and the extinction probability is less than 1. Calculus tells us that this means g prime of 1 is important. What is g prime of 1 then? The series of g of z and g prime of z are here. Plugging in z equals 1 in the second formula for derivative of g, we get g prime of 1 to be this. If we add 0p0 in front, it will not affect the sum, but it allows us to see that g prime of 1 is sum of terms of the form probability of x1 equals m, which is pm, times m itself. This is again in the form of weighted values, and in this case, the sum is the weighted average of x1. This means that g prime of 1 is equal to the weighted average of x1. Going back to the two different cases, we can now replace g prime of 1 as the expected value. Suddenly, this makes intuitive sense. In this first case, on average, each infected individual spreads to fewer than one other person, so it is no surprise that the extinction probability is 1. In the other case, on average, each infected individual spreads to more than one other person. Then it is entirely possible that coronavirus will spread forever, hence extinction probability less than 1. This is exactly the same kind of concept that we have met in the SIR model. This ratio, or the basic reproduction number, is precisely the same concept as the weighted average of x1, the number of new cases per case. So whether you pick the deterministic SIR model or the stochastic branching process, you always end up with the concept basic reproduction number. And the common conclusion is that we want to make this less than 1. But this number is on average, so even if one infected individual does not cause new cases, it does not help. Because if everyone else spreads coronavirus to more than one other person, then this ratio will still be larger than 1. In other words, everyone should take this seriously. The next video will be about the inevitable limitations and some possible improvements of this particular mathematical model, as well as the historical context that prompted the 3 mathematicians to study this kind of model. This will be again released in a few days. If you enjoyed this video, please give it a like and subscribe to the channel with notifications on. See you next time!